Everybody. Everything seems a little bit quiet and tame this morning. I know it's a stamina we need for this week. It's a marathon week, but a wonderful week as well. So I hope you've made new connections, and I hope all of the conversations are flowing smoothly now. This morning is a very important set of conversations because, of course, without the prospecting, without the mapping, we don't know what reserves are actually there. So it is a lovely set of conversations that will be chaired by May Martin, who's come from ESA in Harwell in the UK, of course, and she's going to lead all of the speakers. So I'm going to hand over to May in just one moment, and to encourage you also to continue to look at the posters. I know that we have a certain number of votes, quite a number of votes actually, but of course, to make it as unbiased a competition as possible, we need more votes. So please do go and look at the posters through the coffee breaks after the tech demos, because we have very busy, just to map out the day for you before we go to mapping the moon. We have in every coffee break, we have a tech demo. We also have things going on in the Sigma room, but I'm glad you're here in the plenary room. We also have 2 workshops going on in parallel, so there's all sorts of options for you today. So do keep an eye on the program, but of course, we are always very happy if you're here in the plenary room. So thank you for being here, and I now hand over to May. Thank you.
Good morning, everyone. Thank you very much for being here. I'm here to welcome the first set of panelists in the first session today called Prospecting Lunar Resources. This will hopefully be a great set of talks about the lunar resources that we can find, that we can map. And without further ado, I'm going to hand over to our first speaker. But just to say really quickly, each of the talks will be 10 minutes with 2 minutes of questions, and then we're going to progress through the talk systematically. We're not going to have a big question session at the end. So please do ask your talks at the end of each presentation. Ask your questions at the end of each presentation. Without further ado, I'd like to introduce Abigail Calzada Diaz. She'll be talking about from exploration to prospecting, mapping lunar resources. Thank you very much.
This one? No. Okay. I use this one. So, hello, good morning, everybody. I hope that you have a restful night last night. So, it's hard to be the first one in the morning. So, what I'm going to talk today is about how we move from prospecting to exploration and how we actually can support the lunar resource assessments. So, the first thing that I would like to clarify is what is the difference between prospecting and exploration? Because sometimes we use it indistintly. We use prospecting, exploration, as if they were the same. But actually, in the mining industry on Earth, there is a clear distinction. So we have prospecting, that usually is the way to identify or to indicate, to see where the materials that we are interested in are. So usually this type of process, it covers large regions, and we have a low resolution, usually a lower resolution, and we have higher uncertainty. So we know that there is something there is some indication that something is there, but we are not sure what, how, and in what form is there. And then we have the second phase, that it's exploration. Once that we have the indication that something is going on in a location, that maybe in some procellarum there are some indication of rare earth elements, then we move to exploration. And for that, we need to be more focused. We have to reduce the area that we are looking at. Also, we explore all the information in higher resolution. And actually, the point of all this process is to load the uncertainty. So be more sure of, with more confidence of what we are looking at. So in that phase, we actually are moving not just for seeing where these resources or these materials are, but actually to quantify how much is there and actually how much we possibly can recover in the future. So for doing that, the lunar resource assessment, it's done usually by integrating different and multiple data sets. But here there is a catch, there is a problem. It's like we have different types of data. We have spectral data, we have neutron spectrometers, we have gamma ray spectrometer, we have radar, we have many types of data. Each one has its own characteristics, and each one is measuring a specific physical characteristics of the materials. But also we have different spatial coverage. So some of them are covering globally, other of them are globally some certain regions, maybe the poles, or maybe just a specific, or maybe we have an instrument that unfortunately couldn't run more and it didn't have time to cover the entire moon. And also we have different spatial support. So spatial support is also what we can say, what we know as a resolution. So it's actually the size of the pixel that we are looking at. So these are some examples. I'm not going to go through it, but it's like we have data from multispectral, hyperspectral, neutron, gamma ray, radar. We have many types of data. And what we can see is like actually in the spatial support of the spatial resolution, something like that, we have a huge difference. So actually we have something that it goes from tens of meters to hundreds of meters, and suddenly we have others that actually is tens of kilometers. So that is a big problem because we have to put it together some way that actually it has sense and it doesn't show any artifacts or it doesn't mistake, we don't mistake what we are looking at. And also it's like, so yeah, in this, I don't want to go very deep into that, but we can see that all of them have its advantage, but also it has some limitations. So in general, in the current situation of the lunar orbital data, so we have 4 issues. First is like the scale inconsistency is structural. So each data set, it has a different spatial support. Also, the measurements are indirect. So we are not looking at the minerals itself, like if we take the material and actually we analyze it through a microscope. What we are analyzing is like how the material behaves under different circumstances, like of the light, or how they react to the gamma rays and the neutrons. Also, it's like beside the uncertainty that is driven by the instrument, we also have other uncertainties, like the integrations. For example, if we want to integrate some data sets with 5-meter resolution and another data set with 15-meter resolution, when we integrate it, it's not magically 5-meter resolution. So actually, we have to do some work on that introduce also additional uncertainty. And also, it's like in most of the case, processing drive outcomes. So in some situations, we have the same data set, and 2 people can reach different conclusions. And so all of this are things that actually we cannot change. It's what it is, and we have to deal with it. But we can have some control, and we can have some nice attitude, let's say. So it's like we can work in trying to make the scale explicit, so understand what is the support and model how we integrate those data sets to avoid these false precisions. When we combine them, we can make assumptions transparent. We need to be clear of what are the assumptions that we are making. We have to manage the integration of them, but we don't need to force it. And actually, sometimes we have different data sets that they show conflicting signals. So we have to also be aware of that, and we don't force it. We need to track uncertainty as a product. So uncertainty is not something that is there, but actually is something that we need to show, because that is really important, especially when we are considering what risk are we taking when we do a mission or when we invest in a mission. And also, we need to standardize workflows when possible. We need to be sure that we compare apples with apples and not different things. So as long as we can reduce standardize the workflows, we can reduce the variability that is included by the processing choices, how we decide to process the data. So in the last 3.5 minutes, I'm going to talk a little bit what ESRIC are doing about that. So up you can see like the process workflow from the data acquisition to the decision of going to a location to do a mission, including the resource assessment. So currently at ESRIC, we have 2 main projects. One is the lunar resource reference model that is supported by the ESA. And actually that covers most of, I'm going to talk in a bit about what it is, but actually it covers most of this workflow, from the processing to decision. And I put a little line here to data acquisition because actually it can help to support and to choose the data acquisition strategies. And then we have the node graph architecture for geospatial information. That is a new project that we are starting now. So this is a little bit of the lunar resource reference model workflow. And in the center is the lunar data repository, when we have observational data sets, analytical layers, metadata, but also we include the uncertainty, and we are very clear that we need to track from where that data is going and what are all the process that has been done on it. So also we will include a spatial and 3D modeling that we will talk in the next talk a little bit about that. And obviously for the people, we'll have a nice user interface that they can access and visualize the data products. So all the data is the current data that is available, and actually they are access to the NASA PDS or other repositories already. And then we have a node-based graph software for building geospatial processing and resource exploration workflows. So in this case, it's a new way of actually manage the processing and make things easier, faster, and also very traceable. So it's a new way of actually, I cannot give you too much details. Hopefully next year I will be more into the details of actually how it's going, and we can actually show you something. And I just have 1 minute, so I'm going to go quick around about this. So it's like the key takeaways that I would like that you keep in mind during the entire Space Resource Week and from now forward is like, to conduct the lunar resource assessment, we need to integrate multiple data sets, but this data set is different. They are not directly comparable, and there are differences in spatial coverage, data type, and resolution. Consistency and traceability of the process requires a structured and a standardized workflow, so the data are processed and we understand also the assumptions that are made during this process. And finally, at ESRIC, we want to work, and we are working across the entire resource exploration workflow. So informing the data acquisition strategies, structuring the lunar resource assessment, and also obviously supporting decision making. And with that, it's like I just want to keep that in mind. It's like for prospecting to exploration, the challenge is not more data, that we welcome more data, but also data that we can integrate and we can analyze together. Thank you very much, and I'm open to any questions now.
Thank you, Abby. Perfect timing. Do we have any questions from the audience, please? Yeah, hand down here, thank you.
How do we calibrate the data sets? There's multiple data sets that are now emerging. How do we calibrate with the right ground truthing of which is the real data and measurements that the instruments are making, that the data is accurate, and that the implications are valid?
Okay, well, traditionally the data sets are calibrated using the Apollo samples, because actually they are the only samples that we have from a known location. So actually the best way, and that is something that maybe I skipped to say, is like this is just the first step. So actually data analysis of orbital data always are going to bring uncertainty. And to reduce to the maximum uncertainty, we need to go to the next phase. And the next phase is actually going to the moon and take samples from there. And samples from known locations and understanding and what we are looking at. So it's like, unfortunately, we cannot use orbital data for everything. This is just a first step. We need more ground truth.
Thank you. Any further questions? Okay, I have a question.
Okay.
You mentioned about getting more data products. If you could choose any kind of data product from around the moon, what would you like to have that we don't currently have?
It depends. It depends of what I'm looking for. And also it depends on what data I already have available. So actually this is not like many people ask that question thinking that one answer is going to say, is like, the question I hear is like, what single data is going to solve all of your problems? And unfortunately, there is not single data that can solve all my problems. It depends where we are going. It's not the same if we want to land on the moon or where. It's not the same depending on the type of resources we are looking. And also it's not the same if what you want is to actually reduce uncertainty for investment. So it depends. I'm sorry, I cannot give a more detailed questions.
That's okay, well answered. We don't have any more time for questions, but thank you very much, Abby.
Thank you.
Okay, I'd like to welcome our next speaker, Carolyn van der Bogert. She's from the University of Munster and will be talking about geological mapping as a way to further our understanding of lunar resources.
Thank you, May. So we just heard a lot of exciting information about using lunar data sets and making new tools to make that interaction with those lunar data sets much better and more ways to interpret the data. I'm here today to go back and describe an old method for making a higher level data product, and that's geological mapping, specifically geomorphologic mapping. So today, a geologic map, what is this useful for? I mean, it gives you a graphical interpretation or a simplification of the geologic history of that area that you're interested in. And it defines the locations of different geologic materials with an understanding for geologic processes that are going on in that area. And in the end, you also get information about the age relationships between those different units. And this information, although it's an old tool that you have in your toolkit, is really useful for mission planning and design, for operational planning and risk management, and also particularly relevant today, resource localization and assessment. So what data do we use to make a geomorphologic map? We don't actually need a lot of different data sets. The primary data set is an image data set, for example, from the wide-angle camera, narrow-angle camera from the Kaguya terrain camera, for example. And often we also add on top of that as a layer, a digital terrain or digital elevation model. And for the very shadowed polar regions, you can use the DTM to make a hill shade, which allows you to see the terrain in a synthetically created solar illumination angle. So just by using those three data sets, we can construct a geomorphologic map, and how we do that is a geological thought process. We're looking at defining different geological units based on their morphology. So for example, we have the flat, very minimally cratered mare units that would be one geomorphologic unit compared with the rugged, heavily cratered highland materials. We can also add into that definition process albedo. So the mare units are dark. That's one of their characteristics. We might have flat, smooth surfaces that are light colored in other parts of the moon. Those are defined then as light plains units. As the process of identifying these units in your map area goes along, you're going to end up putting them into a stratigraphic position. This I'll come back in just a minute to. And I also added composition here in parentheses because albedo, of course, is affected by composition. And often what we ended up using in our geomorphologic maps is iron and titanium content to help divide mare units into individual units. But the primary focus of a geomorphologic map is simply defining morphologic units. So at some point we have to draw lines between these different units that we've defined. And so confirmed contacts or contacts that are really easy to see, for example, between a mare flow and the massif of highlands material that it abuts against, we can use a solid line to define that contact. Now, there are some geologic processes that make a diffuse contact, like a crater ejecta blanket. And there, we're going to need to draw a line somewhere, but we don't know exactly where it specifically ends because it's a gradational contact. So we have a dotted line that we can use to draw that contact. So the decisions that are made about where and how to draw the lines requires a geological interpretation as that process is going on. And finally, we can add 2D structures onto this map with specific line work, for example, faults or the crater rim that give additional geological detail to that map. So I said I wanted to come back to stratigraphic relationships because I'd like to get all of you who aren't geologists kind of thinking about the geological principles that are fed into making these products so that you can understand better when you want to use them for your own purposes. So here we're going to take a look at a cross-section, a cut through a cake of mare basalt flows. So you have a sequence of mare basalt flows that are coming in over time, and the principle of superposition is that the one at the bottom of that stack must be older than the one at the top of that stack. The next thing that you can think about is, okay, we know that mare basalts are emplaced horizontally, okay? That is the principle of original horizontality or lateral continuity. And so if I go to a stack of mare basalts later on and they are not horizontal, I know that the geologic process has occurred to change their position. Now, the next principle of inclusion is more applicable to sedimentary geology, but for example, if you place a younger unit on top of an older unit and it rips up pieces of that older unit and incorporates it into the younger unit, that's called inclusion. So you can also get age information from that situation. And finally, if our stack of mare basalts get cut by a dike that then erupts onto the surface, then that dike must be the youngest of the processes that we're talking about in this example because it cuts across all of the older units. So now that I've got you thinking about this geologically, maybe you can see the geomorphologic map with a new eyes and understanding that it's showing you the geological processes and history of processes in that region. Now, of course, when we're making geologic maps, we also want to apply standards so that you can transmit your understanding of the maps across different map makers. And so we have symbology, nomenclature, stratigraphic systems that are defined that we then transfer between maps. We also try to use standard unit colors, but sometimes the amount of detail that ends up being included in a map requires us to depart from that standard. You can find information about standards from USGS mapping standards, from the Federal Geographic Data Committee symbology, and we also had a EU project plan map where we worked on mapping standards as well. So when we put all of this together, let's zoom in a little bit more on this map that we've been seeing through the whole talk, and you'll see that there are components that are there to help you understand the map. There's the key that shows the symbology for the different line work, the different kinds of contacts, the crater rims and things. And maybe even more important than that is this column that's in the middle. This is the definition and the short descriptions for each of those geomorphologic units that we defined in the map. And the one at the very bottom is the oldest one, and the one as you move towards the top are getting younger and younger. And those relationships are based on these geological principles that I just talked about. So when you're looking at doing a global or a regional study, you can actually then leverage many different maps to get you a global view. Here, an example of a 1 to 500,000, a map of the SPA Basin area. You can zoom back into the Amundsen crater region, this familiar map again, to get a regional view at 1 to 100,000. And then you want to land somewhere and maybe do some polar science at this location. So we zoom in and we make another more detailed map for the landing site level. and here 1 to 30,000. So here, scale is important with the data sets. Scale is also important with the geological maps. The landing site scale map is going to give you things here. The little white dots, for example, are boulders and the outlines of the crater rims that are in that area so that you have more information for your operations. And I want to leave you also then, second to last, this other view of the importance of scale for the geological maps. You can see in the global map, there's not much detail, but when we move over to the very local 1 to 30,000 map, that's where you get all of the details that you need to plan your activities on the surface. So I hope I've been able to give you a view into what exactly a geological map is, a planetary geological map, that it's going to give you an interpretation or a simplification of the geological history of that region, and that you have to also be careful about the scales of the maps that you're using to plan your activities. And these are powerful, although old, tools for resource localization and assessment, as well as planning. Thank you.
Thank you, Carolyn. Do we have any questions from the audience? Yes, down here at the front.
Stephanie Howell, University of Manchester. Thank you. I think that was a really important talk. I think a lot of people might want to know where you can find these maps, like what resources are available.
Right, there are many maps available across many platforms. A lot of the maps that we publish are actually in the peer-reviewed literature. And so if you just do a search for like Mons Mouton map, then you will find our publication. The USGS has a lot of the older maps. You'll see the one that I'm showing here is the Unified Geologic Map. It's also in the LROC Quick Map web interface. We have been putting together from the Institute for Planetology a Zenodo community for our institute, where we have the maps also available as geotiffs, the ones that we have produced. Another really important resource is the old Plan Map website, and also there was a new GMAP Europlanet program where we did a sequence of planetary geologic winter mapping schools. If you just search that, you can find a lot of online material about how maps are made, what data sets are used, how to process those things. And feel free to talk to me later for more information.
Thanks, Carolyn.
Thank you. I think that was a really important question. If you're happy, I think we'll move on to the next speaker.
Yep.
Oh, is there one more question?
There was one more.
Is there one more question?
Quick
Sorry,
question.
very quickly. Yes.
Hi, nice talk. So, Ciprian Popa from Naples, Italy, National Institute of Astrophysics. So you used a lot of interchangeable terms like geomorphological and geological maps. So are these geological maps on the moon more close to geomorphological map or are more close to geological map? I mean, you said initially that that's an old tool. The geological map is an old tool, but I would argue that that is the tool.
It is the tool.
Exactly.
Yeah.
So are these maps closer to a geomorphological map or are closer to a geological map? Through geological map, a final product of a national service like US Geological Survey.
Right, yeah, I mean, that was one of the purposes for this Plan Map and the GMAP program, was to try to have a national, sort of a European clearinghouse for some of these maps. And it's true, the geomorphologic maps differ from if you have a spectromorphologic map. And the geologic maps that you have on the Earth, of course, have a lot more detail, and we can do a lot more ground truth. Here we go. We need ground truth to turn the geomorphologic maps into real geological maps. Thank you.
Yeah.
Thank you very much, Carolyn. I'd like to welcome our next speaker, Clive Neal from the University of Notre Dame. He'll be talking about the International Lunar Resource Prospecting Campaign. Thank you, Clive.
Good. Yeah, these lights are an exploding sun. It's quite impressive. Good morning, everybody. This is an exciting week. There's been a lot of good information been imparted. We've had the NASA ignition roll out on the 24th of March. We've had Artemis 2, and this is quite an amazing time to be alive. And for us old farts that are around during Apollo, it's having some flashbacks has been quite impressive. But one thing we haven't done a good thing about is actually understanding the resources on the moon. And so I want to give you an update of what this group, the International Lunar Resource Prospecting Campaign, has been up to. And it's very difficult to get things done without money. And you're going to hear me talk a little bit about that. But I also want to give thanks to the other folks listed here that form the steering committee for this initiative that we're putting together, because they are the brains and I'm the figurehead. And that will become evident as we go through this talk. So, is the investment in ISRU technology justified based upon our current knowledge of lunar resources? And I'm going to say no, because there are assumptions that are out there, and I'm going to give you 3 examples of where we've got great technology that may be irrelevant in the lunar scenario. So we'll start off, let's talk about oxygen from regolith. Well, this must be a reserve because it's everywhere on the moon. And as you can see, the 3 different types of lunar regolith have about the same amount of oxygen in them. But will this work in 1/6 gravity? In order to get molten regolith electrolysis to work, you need buoyancy forces to get the bubbles away from the anode. Otherwise, the anode gets oxidized, and that will just degrade it, and they're rather expensive. But it also means that if you cannot liberate those bubbles away from the anode, everything stops, and we don't get a good separation. And you can see there some of the literature that has studied this, and we really need a tech demo on the lunar surface to actually prove that the investments made in this technology are actually worthwhile and it's going to work. Well, let's talk about helium-3. We've been doing a lot of talking about helium-3, and I don't know whether Gary is here, but you can ask him questions about that because he got a lot of questions the other day. But I set this up. We've got a helium-3 map up in the top right there from Kyung Kim's work in 2019. And what we're dealing with here is surface maturity. We are looking at I would say the age of the regolith. Is it mature? Has it been exposed to the solar wind and the space environment for a long time? And you can see there in the Apollo 17 deep drill core, this I sub S over FeO, which is basically a ratio of metallic iron to iron oxide. And you can see the variability as you go down that core. Now, this is a good example of, helium-3 is going to make a lot of money on this, because you can see that as you go down that core, it gets more mature, which means more money. Yes, we like money. But what we see from the map, that is giving you a depth of about 150 nanometers. You cannot extrapolate that to depth, and that's what the diagram on the left there with the deep drill core is telling you. So if we look at refining water ice and creating rocket fuel, our 1 point of ground truth about water ice on the moon comes from L-Cross, and that's a 25-meter pixel. A 1 data point. And what does it tell us? That the volatiles at the moon, the ice in Cabeus crater is impure. So we're going to have to refine it if we want to use it for life support. We want to use it for other things such as rocket fuel. But distillation is the separation process based on boiling points. But the physical separation and collection of the water requires gravitational forces. And if we're producing rocket fuel by electrolysis, we know that in reduced gravity, the efficiency of that process is reduced. So the fundamental assumption behind all this wonderful ISRU technology, and it's going on in the room next door, could be flawed, because they're making the assumption that we can get lunar resources are extractable and accessible, i.e. we've got potential reserves on the moon, and we really don't. So proving the reserve potential of lunar resources is the fundamental goal of the ILRPC. And you can see here that reserves are a smaller portion of the resource because it has to be extractable, it has to be accessible, it has to be in sufficient concentration that you can create commodities that people want to buy. And the economic aspect is one of the roadblocks in the ISRU value chain on the moon. There is no demand for these products as yet, and the only one that has a price point is helium-3. $20 million per kilogram. Is that enough? Do we have a reserve on the moon? We don't know. We need prospecting, and we need more detailed data sets to actually show that. Now, NASA's architecture definition document, the recent release for the 2025, has actually quoted there, ISRU starts with resource identification, characterization, and mapping. And as yet, there is nothing at NASA that will allow us to do resource prospecting. There is no funding available to get it done, yet it states in this document that this is what needs to happen. So there's a big disconnect there. And 2 data gaps have been identified, both from orbit and on the surface. And this is a really good indicator of what needs to happen, because in order to inform the architecture, we need more data both from orbit and on the surface. So we had 2 workshops in 2025, one after this meeting last year, and another one after the Space Resources Roundtable. And these have given us quite a list of things to do. Data mining and analysis, we've got to identify the relevant orbital data sets. We need to start integrating those to define what I call hot prospects, and give that a definition and identification so we can direct mobile surface assets to go ground truth them. And there's the ground truth word. It's quite a nice word. We need lots more ground truth. And we need to define standards for data set integration so that once those standards have been honed into shape, anybody can do it, and we can get a product that is comparable with what other groups are doing. We integrate the ground truth data to improve our predictive orbital data sets to make that better. So this is a living process. It's an iterative process. It's going to take time, and it's going to take collaboration. And then prospecting campaign surface measurements need to be defined, and accessibility and extractability become really key as we do that. So integration of diverse orbital data sets is necessary to locate hot prospects of lunar water ice. And there you have it. There's the table of the data that we've pulled together from previous and current ongoing missions that could be really relevant to getting these integrated products together to define hot prospects. And this is our definition. I'll just read the first bit. A lunar hot prospect is a location where an enrichment in a resource has been detected in independent data sets and is accessible by any viable technology. So we move on to the next one. Standards are needed for lunar resource prospectivity, modeling, and mapping. And you can see here this has been started by Josh Coyen's work in 2025 for the Viper landing site. And it's important for reconciling different geodetic reference frames. There needs to be a way to convert those so that we know we're integrating data for the same location on the moon. And we need weighting criteria for those data sets in order to get to a prospectivity certainty or uncertainty. And this is the process, fuzzy logic. What a great term, fuzzy logic. I love that. I don't know what it means, but I love it. So come talk with me about collaborations on how to do this. And this is our test case, the Gerlache crater. And we are integrating those diverse data sets. And I forgot to mention, I highlighted the 2 meter per pixel Chandrayaan-2 DFSAR data. And you can see on the left there, we've got the coverage of that 2 meter per pixel mapping from Tathagata Chakraborty from the Chandrayaan-2 mission. And you can see that that correlates with a neutron suppression and also surface detections. So I'm over time, so I will go through this quickly. Here are our data sets that we need from the surface. You can see here that in the architecture definition document, we've got requirements for data from orbit, and we need to get these data to lower the uncertainty of the audible data sets to make it more predictive. And OASIS-1 from Blue Origin and the Laszlo mission from DARPA is going to be critical to do that. So, final slide. United Nations, as we've heard, is developing a regulatory framework for space resource activities, and they will report out next year. And this is a problem because we don't have the data to inform them on that regulatory framework. So, what we're trying to do is to make that, and we're convinced them that this needs to be enabling. And Stephen Freeland was up here saying we need to have an enabling regulatory framework. So not only can we get the data that are necessary to do that, but we can do this in an internationally collaborative way. And that is something that I'm really passionate about. So come talk to me, come join us, and let's go dig in the dirt. Thank you very much.
Thank you, Clive. Do you have any questions from the audience?
Yeah, you're all convinced. Love it.
Question down here at the front.
How would you say I feel like a lot of the data that has been shown today has been surface data.
You're right, you can't.
A lot of the data that has been shown today and that everyone has been talking about is surface data. What is the work being done currently in trying to integrate that to characterize the subsurface?
So what we're trying to do is to use those independent data sets that will give us, at least in the polar regions, that show surface and subsurface indications of water ice. And we need to integrate them in a way that we can get a prediction or a certainty percentage. And those that give us a high confidence or a higher confidence may not get anything when we integrate these data sets, but what it will tell us, it will specify the data that are needed from orbit. It will help then inform Laszlo and the OASIS-1 of what they need to do to get the data. And then if we do find a hot prospect, there are rovers in production. UAE has their Rashid 3 rover. That could be, we could talk with them, and I have talked with them about getting, you want to be part of something bigger, and we find a hot prospect, you can send your rover to check it out. And so that's the thing. It's directing the investments that are currently being made so they can be more productive.
Thank you. Any other quick questions? Yeah. Oh, I'm sorry. Down in the front here.
Just a quick...
Oh, okay. I thought you wanted to talk. So, Clive, thanks for the great talk. It is very important. And there was one very important slide where you showed the profile of helium-3, the vertical profile. It went quite fast. Could you just come back to that slide? Because I think this is really critical to understand feasibility of prospecting the third dimension. So
there's a lot of crap here. There we go, that one.
Oh, yeah. So it looks like so this is not helium-3, this is just...
maturity. It's maturity, it is not helium-3.
Okay.
But you find more helium-3. Helium-3 is positively correlated with that I sub S over FeO ratio. So you show that the more mature your regolith is, the more helium-3 you get.
Is there any direct data on helium-3 from those cores?
There are, but they're old data, and I'd have to go dig it out for you.
Mm-hmm. Okay. Thanks a lot.
Okay.
Thank you. Thank you, Clive, again. If you have any further questions, please go and find Clive afterwards. I'd like to welcome our next speaker on stage, John Pereira Nunes II from ESRIC, who will be talking about rare earth elements in creep materials. Thank you.
Good morning, everyone. So my name is John Pereira. I'm working at ESRIC right now, supporting the development of the Lunar Resource Reference Model. And I'm going to talk about a preliminary resource estimation for earth elements in the creep deposits, the Bossa Nova target. So, why earth elements? Nowadays, we are living in a green energy transition that require even more earth elements demand for earth supplies. And in the moon, we know there is an anomaly. There is an anomaly in the creep terrain, creep procellator terrain, that shows high concentrations of thorium, potassium, and uranium. They are not earth elements, but they are friends. They have geochemical affinity. So where thorium is, earth elements are together. So this enrichment was also confirmed when the Apollo samples were brought back to Earth. So we know the earth elements are there. So what we did, we choose the most higher thorium anomaly within the crust, and we separate 3 targets, and we're going for the first one here, which is the Bossa Nova one. And the point is here, when we look at the point of view of space resources exploration, it has been said here that we need more ground truth data. Everything is based more in a coarse resolution remote sensing data, a few samples that were collected during the Apollo missions, and a few meteorites that we have available. So the most important thing is that lacks qualitative and quantitative descriptions of these resources. And when we look for the workflow in terrestrial industry, we see this is the first things that it has to be done. You cannot go after resources if you don't understand its locations, its concentrations, its genetic model, how it forms. So we focus here in trying to mimic this terrestrial workflow using the data that we have. So how we can put all these data together and extract maximum of information possible from this. So we came off this stage of that we call early exploration, and we're going to use an assumption-based scenario and all the data that we have to try to model and estimate these resources. So assumptions play a big role in this case. We cannot run away from this, but we have to make sure that we are selecting robust assumptions. So we have to make sure they are geologically reasonable, they are consistent with the available data, they are supported by terrestrial analogs, sample, and they are conservative since the uncertainty is high. So let's start here. Thorium is usually associated with earth elements. Okay, we know about this. And relative high thorium lunar samples also shows high concentrations of earth elements. This is proved by the samples. Incompatible elements, that how we call earth element, potassium, thorium, uranium, we call incompatible elements. They are incorporated in more evolved magmatism. And we see evidence of this more evolved magmatism when we look to this sample called Sa 169. This is a meteorite, and this meteorite has a clast that has almost 6% of its volume of apatite and merilite. And this class shows association with intergrowth of quartz and feldspar, alkaline feldspar, which is consistent with more evolved trend of magmatism. So it makes sense that we can use the concentrations reported for this meteorite to make a resource estimate. We have the most enriched meteorite, we are looking for the most enriched area in thorium. So a resource mapping and estimate is only as reliable as the assumption on which it is built. So the first thing that we have to start before anything is with the geological map. Carolyn already addressed this here. And so I'm not going to repeat again the importance of the geological map, but it's just to emphasize here the geological map is not just beautiful colors in an image. It's extremely essential. But here, in this case, we change a little bit the approach. The maps that you saw relies more in morphologic aspects of the region. So we try to make more, as we did here on Earth, using the data that we have. We have some mineralogical maps that shows the concentrations of few minerals that we can use to assume some lithologies. And this is important because even in a regolith-dominated scenario, like the lunar environment, lithological map helps to identify bedrock's affinity, magmatic relationships, and potential controls of this mineralization. So here you have like a totally new version of this map. Here are all the critical data that was used to define each unit. I'm not going in detail of each unit and detail each one, but I don't know if you can see, I hope so, because that's why it's green neon, but there is some spots that are green neon here. And these spots were delimited based in some hyperspectral analysis that we did, some preliminary hyperspectral images that shows that some neodymium absorption bands potentially occurs in this stage, in these areas. Plus, it shows that these areas also show relatively low crescent feature, which is this map here in this corner. Crescent feature can indicate where more involved magmatism can occur, and this is related to rare filaments. So basically, we defined these targets, and then we did a 3D geological model, which is the basis to start to estimate something. For this, for the estimate modeling, we use an implicit software tool called Leapfrog. It's very known in the mine industry, and the software creates the structural data, and they make everything by their own. And so we have the interpretative volumetric of each one of the units that we consider important in this scenario. And with this, we create also a numerical model. This was more like a test, which is a scenario. We use the gamma ray spectroscopy data from the Selene and Luna prospector. The first one is only gamma ray data, and you can see that there is a trend to concentrate more thorium. We use just thorium. In the highlands of this area where marine basalt has lower concentrations. Here in this one, we decided, okay, let's assign the concentrations that we have for that meteorite in one of these phases. And we have something like this corroborating that the high thorium are associated with these topographic crests that you see in the area. Oh, sorry. So after this, what we did was, we have these evolved phases, and we discretize these evolved phases and some cubes of 50 by 50 by 50 meters. And for each one, which we call black model, and for each one of these cubes, we assign attributes, describe its density, its concentrations, and I'm going to explain later. Also, you can see here is those blocks. I think you can see the small blocks in the image. And when you take in consideration only the units that was mapped as potential rare filaments, you see there is high concentrations of thorium in this topographic crest as well. So what we did here, we apply a weather model in this topographic crest when 10 meters are regolith and 40 meters are fresh rocks. We know that it's not fresh, it's extremely fracturated and so on, but it was just to simplify the model at this stage. And we assign for each one of these blocks, if it's fresh rock, we assign the density of 3 kilograms by centimeter cube. Everything was based in the SAL 169, and the results reported for Lin et al. Also, we assign the concentrations of rare elements of apatite and merilite with yttrium, cerulitanium, and neodymium concentrations. The other rare elements were not measured by the author. And for the regolith was the bulk content of rare elements in the regolith for the same meteorite and the average density of the meteorite. And with this, we reach a scenario. With this scenario, we reach that we can expect to extract 236 kilotons of rare elements within this crest in the regolith, and together with the fresh rocks, almost 13K kilotons of rare elements. Of course, there's a lot of assumptions in this model, so we have to take care about these numbers. And we compare this grade and these numbers with other terrestrial deposits to see, like, okay, if how we can compare this grade and with the terrestrial setting. And we look here in the A, we have the South Africa deposit in Mountain Pass, which is essentially magmatic deposits, and they are very high compared to Bossa Nova. But then we have to remember that this assumption is based only on content of apatite and merilite, just 2 phosphates. So, okay, let's check how is compared with phosphorus deposits on Earth. They are not magmatic, they are essentially secondary deposits. But if we compare this grade of Bossa Nova with other ones, we see that actually it's relatively high. It's just only with the exception of the Mississippian phosphorate deposits on Earth. So for now, with all these assumptions and all these uncertainties that is inside of this this type of modeling, we consider to classify Bolsa Nova as a low-grade deposit for now, since we don't have a lot of ground truth data and the cost resolution is still a big problem. So why preliminary resource estimate matters now? Because it quantifies the order of magnitude of rare elements potential, it enables comparison between prospectivity targets, it supports prioritization of future exploration efforts, it provides a framework for technical and economic assessment. It's very important. The point here is not to prove exactly the quantity of rare elements you're expected to do, because we cannot do this with all these assumptions that we make. But it's more in the way to support decision making. How areas should we prioritize in this context? And here also more important is highlight data gaps. I think what's been said a lot that we need more ground truth data. We need sampling. We need high resolution surveys, including geophysical surveys as well, because it will help us to understand how these units behaves in depth. And also systematic samples, surface and subsurface. We need to drill. We need the depth information. And the key point is the preliminary resource estimate are decision-maker tools, not definitive resources statement. Thank you very much.
Thank you very much. Do we have any questions from the audience, please? Yep.
Yeah, Clive Neal, University of Notre Dame, a very nice talk.
Thank you.
We know that the thorium is associated with plagioclase in the highlands rocks. Did you do a slope map because it's associated with Imbrium ejecta? And trying to get...
Sorry, can you repeat?
Okay. Yeah, I know it's difficult to hear up there, isn't it?
Yeah.
Did you do a slope map? Slopes, because you've got it at the crest, and trying to get ground truth from surface assets is going to be difficult, if not impossible, given current technology. So I think a slope map added to your excellent geological work would be interesting. But remember that the rare earths and thorium associated with the ejecta from the Imbrium crater. So I don't expect them to be flat, but a slope map would be very enabling in terms of accessibility.
Yep.
Thank you, Clive. We've got time for one more.
Thank you. Jakub Ciążela, Polish Academy of Sciences. So my question is, how did you estimate the abundance of apatite and merilite, and did you also consider other rare earth elements, rich minerals such as monazite or xenotime or bastnazite, maybe? So if you could explain a little bit.
Yes, but the point is use the data that we have from the meteorite. Of course, it can be associated also with monazite, with xenotime and other minerals. But in this case, we choose to go only for the data reported for the meteorite only. And they only have apatite and merilite. It's the only source that we have.
What about Apollo samples?
Yes, but in this case, Apollo samples was collected in another place. So we cannot assign the Apollo samples concentrations for that area.
Okay.
Okay, thank you.
Thank you very much, John. I'd like to welcome Laszlo Kestay, our next speaker from the United States Geological Survey. He'll be talking about for taking lunar resources to reserves. Thank you.
Okay. Thank you all. I'm going to say we need more ground truth, and you can go to sleep now. But I'd like to thank my co-authors. Couldn't have done this without them. And but I'll be talking to you about how we can take resources to reserves on the moon. And so what am I talking about with resources and reserves? So a resource is something that's on the moon that we think we can potentially make use of. Concentrations of resources are deposits, and those resource deposits that we can actually use are the things that we call reserves. That's pretty general, but so let's talk about what are the challenges to get a resource over the fence into the reserve box. One of those challenges are legal, so we have our diplomats and lawyers working on that. There's the technical issues of trying to actually convert a resource into something useful, and the engineers are working on that. Then there's the knowledge, our understanding of the resource, and that's what scientists are working on. And then there's going to be the fiscal challenges. So that's where the economists and hopefully our funding sources will be working on that. So we got many different challenges to actually turn something on the moon into something useful for real. And where are we today? There are some things. I'll suggest that solar power is actually a reserve. In the red circle is regolith, where we have quite a bit of information. Engineers are working on it. It's maybe halfway over to getting to being a reserve in terms of our understanding of the resource. And then in the blue circle is ice, squarely in the speculative box. Let me explain a little bit about what I mean by each of those boxes. So, solar power as a reserve. So, if you're struggling to understand what I mean by the word reserve, think about the way we use solar power. We know how bright the sun is, when it shines, where it shines. So we have a good understanding of it. The technology to convert it into electricity is very mature, TRL-9 for decades. So far, we've had no legal obstacles with people harvesting sunlight to generate electricity. And when the engineers take a look at it and just try to make a decision, do we want to use batteries or nuclear power, or do we want to go solar? They'll look at how much it will cost, how much the mass is, the volume, all the different budgets they have, and decide which is the right technology to use. And if solar is the right way, then that's what will end up on the spacecraft. So we want other things to feel like generating electricity from solar power. Compared to that, where is regolith? It's in that middle box, using the word inferred for that. So what does that look like? We have a good understanding of how regolith is produced, a predictive model. We know that impact after impact grinds up the rock. That's how it's formed. We have lots of different remote sensing data, and they give a pretty consistent map of the variations in properties like chemistry and grain size. We have quite a number of samples from different locations. We've drilled in it, we've driven over it. We have a pretty decent understanding that we can extrapolate from. What we lack that would push it over into the reserve category is that detailed information from a location you'd want to put an ISRU site. So a detailed 3D model from a specific site. It's this kind of study you'd want to do before you send a big plant. You might send a pilot plant without understanding enough, but before you go into production, you're going to want to do a detailed site survey. And where is ice? Well, I'm calling it speculative. What does that look like? Well, right now, we have multiple competing hypotheses. This is a playground for scientists. Lots of different ideas we can go and test. When you look at the remote sensing data, we have lots of different data sets, but they're giving inconsistent indications of where the ice is. And we have one in situ measurement, and I'd call it inconclusive. If you look at the error bars at the 95% confidence level, it's not 5.6, it's somewhere between 0 and 11 weight percent. And then when you look in detail at the ratios of the different elements, it doesn't fit any simple model for where that ice might have come from. So we really fundamentally do not understand the ice. And we're pretty sure there's ice there, but trying to say anything definitive about it is really challenging. Okay, like I said, what I'm going to say, we need in situ data. That is what will move things along on increasing certainty. So in the case of ice, we need the ground truth in order to make sense of the remote sensing data and then hopefully test the hypotheses and so forth and make progress. And like I mentioned, if you want to use a regolith, we want to do that detailed site survey before you put in a production plant. So how much data do you need? You already saw this plot from Josh Koyan, where as you have on the horizontal axis, increasing information, you're able to do more and more complex types of analyses. And we have a proposed standard for defining what a reserve is. We should get geologic knowledge error down to plus or minus 20%. As we go, that maybe that number will change slightly, but the concept is we need to be able to talk about uncertainties, do statistics. And that means on this chart of different kinds of analysis or assessments, we need to get to the probabilistic estimates. So we need to be able to do good statistics. And that will drive how much data we need. So in order to do the basic statistics on how much things vary from one deposit to another, you need to go investigate at least a dozen deposits. And within each deposit, if you want to get each parameter reasonably well defined with confidence intervals on your basic things like the means in there, you're going to need tens of measurements. If it's well behaved, around 30. So you need hundreds of measurements from different locations. And the good news is if you go with mobility, with rovers, you may be able to investigate multiple deposits in a single mission. So you might not need 12 missions, but you need to investigate a good-sized area. Exactly how much area you need to investigate depends on how things are distributed on the surface. And for like ice, we don't know that. So we can't even tell you exactly how much mobility you need. But in any case, we know we need in-situ data. And that means we need to be able to land and drive around safely. And you want to examine lots of different data sets when you're considering landing site safety and your trafficability. But of all the different data sets, the single most important one will be topography. That's partly because slopes are a hazard in themselves, but also topography is your input into lots of other models, like your temperature models, your illumination models, communication, etc. So when you talk about lunar topography, the foundational reference model for the moon is based on LOLA, the laser altimeter, and in the equatorial areas, we've been able to sharpen that up by combining it with the terrain camera stereo data from the Japanese missions. So that is the reference for the moon for topography. But it does not have the spatial resolution to do landing site analysis. So let me show you, here's a little snippet of where the Viper plans to go. I didn't put a scale bar on it. That's 500 meters from top to bottom. The bigger craters are right around 100 meters across. And you probably can't see. There's little red dots on there for where the LOLA shots are. So let me show you what the same terrain looks like with LOLA. That's what you got. Every one of those data points is exquisitely precise, but we just don't have enough to define the topography at the scale that you're worried about when you're trying to land. Let's go back to the image. But the good news is there are techniques to get topography at the scale, shape from shading. The most reliable software out there right now is AIM Stereo Pipeline. Ross Beyer wrote it. His group and others have learned how to use it well. And you can end up making topography that looks like this. So it's at the resolution of the image data. When you have enough images, please use good topography so you can actually see what you're landing on at the right scale. And let's see, I'll wrap up by just repeating myself. If you're trying to understand what reserve looks like and trying to get a gut feel for it, imagine solar power. For regolith, we're getting close, but we need the in-situ data, the detailed 3D surveys of specific areas. Ice, we've got a long ways to go. And everything needs more in-situ data. And if you're going to go collect it, please use good topographic data. Thank you.
Thank you, Laszlo. Any questions from the audience? Yeah.
Hi, thank you for the narration. My question is why are we calling the regolith as inferred and why not an exploration potential? Do we have enough data density and any reasonable economical extraction possibility in that?
I'm sorry, I couldn't hear all that. You're asking about the regolith, but I didn't hear what about the regolith.
You are calling regolith as inferred resource. So my question is that why are we calling it as inferred resource and not an exploration potential from a resource coding point of view?
Yeah, I'm sorry, I'm going to have to come and talk to you because I can't hear exactly. I'm putting it in the inferred category because we know quite a bit about it, but not enough to use it today on a production scale.
Yeah, I'm really sorry, it's very hard to hear on stage, so if you could speak very closely into the microphone. Do we have any other questions, please?
Hi, my name is Simon Drake from the Lunar Resources Registry. I'm also an early stage investor in speculative mining companies. So my question for you is, how close are you as the USGS coming to turning regolith areas from a speculative area to resource reserve and then potentially an asset?
So in terms of how far along is the USGS in doing the assessments, I'll take it back to Clive's problem. It's the money. I think we've done enough to say we know how to do an assessment, and but we have not been funded to actually do one. So that's where we are.
Okay, thank you.
That's a really good point, thank you. Thank you very much, Laszlo. And I'd like to welcome our final speaker, Richard Palin from the University of Oxford, who's going to be talking about potential ore resources on Mars. Thank you.
Is this loud enough for everybody? Because it's getting quite loud outside. When the presentation loads. Okay, there we go. Thank you. Yeah, please let me know if you can't hear me. It's getting quite noisy out there. Thank you for sticking around as well. I know the moon is the popular body to discuss here, but hope to convince you that we can do a lot of, at least, prediction for the types of resources we might find on Mars, which is quite a geologically interesting planet, of course. So I'll start off by saying we have heard a lot of good research that's being presented at this conference that's related to legal and regulatory frameworks, issues related to engineering and actual extraction of resources from the ground. But before you can actually do any of this, before you can actually mine your resource, you need to know where it is. So this has been discussed by people in this session already. Where do we find these deposits? How large are they? What kind of grade do they have? What minerals do they contain? These are the kind of questions that a geologist is well placed to answer. So I'm a geologist. I study natural resource formation on Earth, how we discover them, how they form, and also have an interest in planetary science. So putting these two things together, we attempted to make an estimate of the strategic resource potential of Mars by using a comparative approach. So I think it's quite obvious to most in the audience that if we understand how ore deposits form on the Earth, and if similar processes have happened on Mars in the geological past, we may expect to find similar deposits at different places on the Martian surface. Earth and Mars started off being created from the same building blocks, so we assume they have similar bulk compositions, and therefore probably similar strategic metal endowments too. So the big question here is, where should we look on Mars for any given deposit type? Now, this entire talk is really an extremely fast and short review of a much larger review paper that we put out at the end of last year. I realize now that Earth Science Reviews is probably not the best avenue to have placed this, but it's where it was accepted, so it will stay there for the rest of the time. I can't cover everything that we discussed in here, obviously, just in a short amount of time here. I would encourage you to read the paper if you have an interest in this, or come and find me afterwards. Very happy to talk about any of these aspects. There we go. So to start off, we need a basic understanding of the surface evolution, the characteristics of the geology of Mars over time. Now, this figure shows the Martian timescale lined up with the terrestrial timescale. And I understand that many of you won't be geologists, but we can break up geological time into large blocks called eons. On the top, we have the terrestrial eons, the Hadean, Archean, Proterozoic, and Phanerozoic. And on the bottom set of colored bars, these are the Martian eons. And I'll very briefly talk over the characteristics of these 4 eons. So there's the pre-Noarchean, pre-N in the dark brown there, the Noachian, the Hesperian, and the Amazonian. These cover different lengths of time. The pre-Noachian is the very early stages of Mars's history, and down below we have characteristics derived from different studies that would match these different points in time. So, for example, magnetic field. It's understood from an analysis of Martian meteorites of certain ages that Mars's magnetic field cessated. It was lost at some point in time at around the end of the pre-Noachian. So you might expect there to be, and we see this in other geological evidence, a loss of the shielding effect of the magnetic field that will hold an atmosphere onto the planet, if you want to treat it in those types of words. This is shown on the bottom half of this figure, which is not visible here. Volcanism throughout Martian history is well understood. We have crater counting of lava flows on the surface. We can see when there was major events of volcanic eruptions and such. This would be of interest if you're looking for magmatic type of ore deposits. Impact history, we have a particular type of ore deposit that we discussed, which is related to impacts. We see examples of this in terrestrial deposits, such as Sudbury, where we have nickel and copper sulfides associated directly with an impact basin. Fluvial and glacial surface activity, so the actions of ice, water, plus minus wind on the surface, can help to move around and make new deposits, sedimentary type of ore deposits. Aqueous mineralogy, I'll cover in one of the later sections. These might come under the category of salts and evaporites. So if you have water on the surface of Mars, which we did at some point in the distant past, and that water is lost, whether it's to space or down into the crust, if it evaporates, you will leave behind salts. And these contain many elements of IRSU importance. Atmospheric pressure is put there as a kind of addition. It's not so important in the context of this work, but we discussed it as a characteristic regardless. One of the main figures in the paper was obviously a map of where we expected certain types of ore deposits to form. All the labels that you see on this map we discuss in the work, and we give our arguments, our geological reasoning, why you might find a particular type of deposit in those places. So once again, time limited here, but please check out the paper for particular deposits of interest. So I'm going to go through, very briefly, these 4 eons in Martian history and just give you a taste of the kind of deposits you might expect to find in rocks of that age. So the pre-Noachian, as I mentioned, at the earliest stage in Mars's history, was almost certainly dominated by impacts, just as we see for the Hadean and early Archean on the Earth today. And therefore, a lot of the discussion in the paper was oriented around impact-related deposits. Now, sometimes we break up these types of ore deposits into 2 or 3 types. A progenetic type of deposit might be one that already exists in the ground, and the impact merely excavates it and removes it, and you can access it at the surface. A syngenetic or epigenetic type of deposit will be one that's generated during impact, so related to the heat, the pressure, the fracturing, and later cycling of water through those fracture networks that can mobilize metals and reprecipitate them in certain places. The Noachian period on Mars, the Noachian eon, was characterized by widespread volcanism, and you still had a climate on the surface which was alternating between dry and wet cycles. This is the period of Mars where people say you had large oceans or smaller bits of oceans that were not connected to each other. It was a wet surface. And of course, in those environments, you might expect to find sedimentary deposits to crystallize or form in bodies of water. An interesting example that we talked about in the paper is an extremely large, like hundreds to thousands of kilometers squared region in Sirius Meridani, which is where you have crystalline hematite. This is obviously a spectrum map highlighting iron, and the interpretation of these data, which of course is debated, is that these might be analogous to BIFs, banded iron formations that we see on Earth in Archean terrains. Hesperian Mars, this is the period of Mars where you lost the climate, you lost the atmosphere, and the water receded and evaporated. And I use an example here simply from Wikipedia, just to demonstrate that these are the kind of areas and environments and rocks of this age you might expect to find evaporite salts in. Now, evaporite salts on Earth contain lots of important elements, which would be even more important from an IRSU perspective on Mars. So elements such as magnesium, bromine, iodine, strontium, potassium, these are very useful elements, for example, for life support systems. Another good thing about sedimentary type deposits is that they're very accessible. They form at the surface of planets. And from an IRSU perspective, accessibility is one of the major factors you would want to consider. The final eon on Mars was the Amazonian, and this is characterized as a period after you have lost the surface water. So you have a very dry surface dominated by aeolian processes, so wind-driven processes. And these processes would create the large dune fields that we see on Mars today. A type of deposit one might expect to find, and we have seen this in certain places, is these blueberries, which probably some in the audience will be quite familiar with. So these are hematite spherules, which are embedded within sedimentary rocks, but the action of not so much water, but wind in the Hesperian or post-Hesperian Mars has removed some of these hematite blueberries and concentrated them as lag deposits in certain places, which again make them very accessible for ISRU purposes. So that was the quickest summary of a review paper I could possibly have done. We had a section at the end of the paper discussing, well, what comes next? Obviously, putting down this theory and laying the groundwork is just the first step. One might imagine that the next step might be to move to a more either global or focused approach, depending on your objectives. In the paper, we argue, just as has been said in previous slides here, sometimes it's best to take a step back. So at the moment, we have information from a small number of landers, sort of been on the Martian surface. So we have you might call it, focused data from a small number of sites, which may not be fully representative. And one of the approaches you can use to bridge this gap is to use orbital data collected from satellites, so remote sensing type of data. And machine learning is a technique that's being used commonly now, at least in terrestrial formats, to make predictions of where mineral deposits may be found. We have started this kind of work in our research group in Oxford. I've had PhD students who've worked on mineral prospectivity mapping using machine learning techniques based on terrestrial deposits. And the next sensible step, in my mind, might be to apply that to extraterrestrial deposits and take this one step further. I'm going to leave you with this final slide just to say thank you for your attention. And also, just to make note, this work is partially affiliated with a new scheme, a new initiative that's been funded internally by the University of Oxford. It's a multi-million-pound initiative called Oxford Earth, which is designed to stimulate research looking at unconventional resources. Now, terrestrially, this might be something like helium or hydrogen generated by serpentinization, or mining brines as an unconventional type of resource. But extraterrestrial resources, I believe, still come under the same category. And we have opportunity to get involved with different projects if you would be interested. So please talk to me afterwards. I apologize for going a few seconds over time.
Thank you, Richard. We have time for a couple of questions before we close the session. Yeah.
Thank you. Thanks. Jakub Ciążela again, Polish Academy of Sciences. So my question is about two other deposits group, whether you consider them and what do you think about them. One would be orogenic ore deposits related to early tectonic processes on Mars, thought controlled, for example, gold deposits, and maybe also alluvial gold deposits that could be related to early alluvial network of Mars. What are your thoughts about this?
Yeah, that's a great question, and something I should have emphasized, I guess, in a much clearer way at the start. Your question is well taken. So plate tectonics and plate tectonic processes would be generating some of these ore deposits. And you mentioned orogenic gold, of course, which is related to plate tectonic convergence environments, mountain building events that happen on the Earth today. So we note in the paper that certain types of deposits, including orogenic gold, you may not expect to find on Mars due to the lack of similar tectonic activity. As for fluvial gold deposits, by continuing that line of reasoning, you may not expect to find them, as some of the gold in fluvial gold will be derived from orogenic type of deposits. It will be an erosive product and deposited in a fluvial environment from those deposits. So there'll be a kind of chain of reasoning to suspect that they might not be apparent too. But I should say this is very speculative, and more research is needed in these fields.
Okay, thank you.
Thank you. Any further questions? That brings us to the end of our prospecting session. I'd like to remind you all there's a tech demonstration at 10:35 by DFKI out in the main area, so please go and check that out. But before we all go, I'd like to thank the speakers once again for their presentations. Thank you.